In this video, I want to look at the definition of the derivative and look at this interactive website that allows us to explore that. So here I've got a function f of x. I'm able to type in a formula here. So let's just start with the default. It's x squared minus 3x. And so we can see that we have a graph of that parabola. There's a point here that I can slide back and forth. It's currently set to x equals 1. So we're going to calculate the slope of the line, of the tangent line at this point right here. The idea of the derivative is that we actually have a second point. So there's a second point here. It's at c plus h. H is measuring the space between these 2 points, and we get to control that in the second pane. So I have a slider here. I can click on h, and as I change this value of h, you'll notice the graph on the left, the blue point is moving with my point. So where I started was at h equals 1, and so we can see that this blue point is 1 unit to the right of c. So we're sitting here at 2. And it draws a line. This is called the chord or the secant line between the 2 points f of c and f of c plus h. Alright, so the idea of the tangent line is what happens when the second point approaches the first point. So I'm going to zoom in on what's happening here. So as I let h get closer and closer to 0, my second point is moving closer and closer to c. You can see that this secant line is becoming very close to the tangent line. And the closer I make h, the closer my approximation is. Well, this app is also calculating the slope. So this slope of this yellow line is given by the rise over the run, the delta f over the delta x. So currently we can see that the value of that slope is negative 0.9545. So let's now zoom in my h graph here. So the closer I get to h is 0, you can see that I'm getting closer and closer to the true slope, which for reference is shown here as negative 1. Now there are some weird things that happen if I get too close. There's a little numerical issue. You can't trust anything here that's really close to 0. But, excuse me. So on either side here, positive and negative h, you can see that the slope is really close to negative 1. So this is the derivative. The derivative is the limit as h goes to 0 of that slope. Alright, so let's take a second point now. I'm going to reset the graph. So this h, and I apologize, the formatting doesn't always update. So let's now look at a second point. Let's look at c equals 0. So let's move c into 0. Alright. And so when it calculates the slope from c equals 0 to c plus h, which is at 1, so I've got these 2 points. Didn't quite get it in there. C equals 0. There we go. So now I'm at, if I calculate the slope between these 2 points, I have a slope of negative 2. And as I let h get smaller, like at a half, you can see now that my slope is negative 2.511. And I just let h get closer and closer so that my secant line is closer to a tangent line. And I'm getting now negative 2.943. We can see the limit. If I let that get arbitrarily small, the limit would be negative 3. So if I come from the other side, again, the closer I get to 0 for my h, the closer my slope is to negative 3. So The graph on the right is actually the slope of the secant line for all these different values of h. So for each value of h, I calculate the slope of the secant line, and I plot that slope, and you can see that as h goes to 0, there's this hole that corresponds to the slope I'm trying to find. And so when I calculate a limit, I'm finding the value of where that hole is. So I want to look now at how we might use this app to help think about our activity, which is going to be a few web work exercises. And so let's take a look at the first problem. Alright, so our problem is considering a function f of x equals x cubed minus 9x. So let's start by setting our function to match that. We have x cubed minus 9 times x. Okay, so here's our cubic. And it says calculate the difference quotient, and the difference quotient is another name for the slope of the secant line, so the average rate of change. So we're going to calculate this difference quotient, the average rate of change, f at 3 plus h, that's my second point, minus f of 3, divided by delta x, which is h. So that's the slope of the secant line. And it has 4 values of h that we want to do. And unfortunately, the app doesn't show enough decimal places or have enough control for us to directly answer the question here. But let's go take a look and see what's happening. Alright, so we want our c value to be at x equals 3. So I'm going to drag this point over here to x equals 3, and hopefully can't quite get there. So we're kind of close. I'm going to zoom in a little. And you can use these arrows to move left and right, or on my computer, if I hold the shift key, click and drag, I can move the pane around a little. Let's see if I can get kind of close to 3. Well, we'll settle for that. This is just going to be an approximation. Notice that my y values have zoomed out as I zoomed in, so I'm going to zoom out y so that I can see my picture a little easier. So here are my 2 points. It's c and c plus h. And I can see a reported value for my slope. Remember that this curve is the value of the slope. I want to see that a little better too, so I'm going to bring this down a bit and maybe zoom out. Okay, so the slope that we're looking for is this hole, and we can see that as I make my h get closer to 0, the 2 points on the graph are getting closer to each other, so my second point's moving in towards the first, and the closer I get, the closer this slope that I'm measuring is to the limit where the hole is. So on the right, my slope is too big. On the left, my slope is too small. And if we were looking, we could see that the slope is getting really close to 18. And because my point is a little off to the side, my values aren't quite right. So what I want to do is I want to go now we've seen what we're doing, let's go to Desmos and we can get a little more accuracy. So my graph is a function, it's x cubed minus 9x. Just verify that I'm doing the right problem. And we're going to be able to take advantage of Desmos' ability to do calculations, and we can actually use this h. Alright, so I'm going to say, what is f of 3 plus h? minus f of 3, all of that over h. And so I have a slider. And so I'm now able to set my values of h. Notice that you can't set h equals 0. My slope is undefined. That would be the same problem here for why this graph has a hole. And I can't actually set h equal to 0. So if I could actually make h equal 0, again, I don't have enough control to get in on that point, but I'm unable to calculate that slope. But I can set h equal to 0.1, and I get a value here, 18.91. So 18.91. Oops, 91. And I can also say, all right, cool. What happens if I go to h equals 0.01? Notice now I get a value of 18.0901. So that's my value here, 18.090901. And so I have these two slopes. And notice as h gets closer and closer to 0, I'm getting a number closer to 18, which matches, if I could have gotten this point on the right spot, the slope actually is 18. That would be the limit or value of that hole. Let's make it even smaller. This wasn't asked for on web work, but if I do 0.01, or 2 zeros in 1, you can see that closer. And if I do even more, the closer I get to 0, the closer I am to the actual slope of the tangent line. And so the limit of this would be 18. So here, the limit is 18. And I'll let you calculate the values of h that are negative.